Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, I did a poll on my main channel, Bob the Science Guy, the other day, and asked what type of videos you would like to see on this channel, Research Flat Moon. Now, one of the more popular subjects that you picked in that poll was an explanation of the thought process of science. You know, I was watching television with my son, and I got to thinking, right now we have several different ways of determining the radius of the Earth. We can use the method of Eratosthenes, where we look at the shadows from a stick. We can use the method of Runi, where we look at the dip angle down to the horizon. And we can measure distances across land following great circle routes. All of these will allow us to figure out the radius of the Earth. But one of the things that we use very frequently is something called the curve calculator. Now, could we use the curve calculator and the amount of a building visible at a known distance? Could we use that to determine firsthand the radius of the Earth? Well, I think I figured out how to do it, and you can all do it with me. So let's cue up the music and get going. Now, most of you are familiar with Walter Bissland's Advanced Earth Curvature Calculator. And basically what you do is you plug in your observer height and the distance to the target and the target size, and then go down here and it'll tell you how much of that target will be visible. Now, the way this works is that you are located at a certain point on the surface of the Earth. You go up to a certain observation height. You look past the horizon in this straight line down to your target. And based on where this line is, part of that target will be hidden and part will be visible. Now, this is a very nice curve calculator because it can include things such as refraction. Now, the Earth curve calculator uses something called the Pythagorean Theorem. And basically, this is the Pythagorean Theorem. We all remember this from school, that when we're dealing with a right triangle, if you take side A, B, and the hypotenuse C, A squared plus B squared equals C squared. Pretty straightforward thing. Well, how does the Earth curve calculator use that? Let me show you. So say you're an observer over here. You're at a certain height above the ground. Now, the distance you are from the center of the Earth here is the radius of the Earth plus the height. The distance to the horizon, which is at the level of the surface, is the radius of the Earth. And our distance between our observer location and the horizon is d. Now, normally when we use the Earth curve calculator, we use this accepted value of r. We know our height above the ground. We know the radius here. So we've got these two sides of a triangle. So we know that radius squared plus distance squared equals radius plus height squared. We know these two values. We use that formula to find d, the distance from our observer position to the horizon. Then what we do is we simply reverse this around and we go over to our building. Now, if we know the total distance between our observer location and the building, it's a simple matter to take that total distance, subtract this d from it, and get the d over here. Now we've got the radius and we have the distance. Once again, all we do is we square the distance and the radius, and it gives us the total height here to where we can start seeing the building. Now, by simply subtracting the distance of the radius of the Earth from that total value, it tells us how much of that building's hidden. Now, here's the problem. What if you don't know the radius of the Earth? Can you figure out a way using this formula to determine the radius of the Earth? Well, as it turns out, you can and you can't. But I got to thinking the other day, and this is what makes science science. how would I determine the radius of the Earth from this? And then I had to sit down and look at it a couple of different ways. Well, it's going to be very difficult for me to do it with both triangles. But if I know the distance to the horizon, it should be pretty simple. Let me show you how that works. So, here's our horizon. Here is our observer location, right here. We draw a line between the two, and we want to find this distance right here. Now, why is that important? Well, there's our triangle. Now, A would be the distance. B, that would be the radius of the Earth. And C, that would be the radius of the Earth plus our observer height. We should be able to calculate the radius of the Earth by knowing our observer height and this distance. So let's go see how that would be done. So I took a moment and I put the values that we're going to use. We're going to use R plus H, and D. From Pythagoras, what we're going to do is we're going to realize that D squared plus R squared equals R plus H squared. Should be pretty straightforward. Well, let's go ahead and see if we can solve for R. So what we're going to do is we're going to bring this back up. So we're going to go D squared plus R squared equals, and instead of using a squared here, I'm just going to save a little time. That's R plus H times R plus H. Now, solving for that, we've got D squared plus R squared equals R squared plus 2RH plus H squared. That's just basic algebra. Now, we've got something that we can work with. What happens if we subtract R squared from each side? Well, it's pretty simple. We'll get D squared equals 2RH plus H squared. Now, we can solve that even more. D squared minus H squared equals 2RH. Now that we're at this point, all we have to do is divide that by 2H. That drops out to 1 equals R. So, if we know the distance and we know H, we can find R. So let's go ahead and give this a test. Okay, so there's our formula again. Now we know that for a 6-foot person, the horizon is 3 miles away. And we can measure that. Now, if we use 6 feet as our height, and 3 miles is our D, that's 3 times 5,280. And there we go. H is 6 feet. D is 15,840 feet. Let's plug it into our formula. So, D and we're going to square that. And then it says minus H squared, H. And that's going to be over 2H. That comes up to 20,908,797. Let's divide that by 5,280, and we'll find out what the radius in miles is. You can do the math with me. It works. But there's a problem with it. What happens if we don't know the exact distance to the horizon? First of all, how would you even find the exact distance to the horizon? Well, one way that you could do it is you could go to a certain elevation above the ground. What is the farthest object on the ground that you can clearly identify from your vantage point? That's one way of finding the distance to the horizon. But is there another way? Sometimes the best way to solve a math problem is to look at it from another way. So let me show you how I looked at it. Well, one of the things that we have to do in science, and one of the things that actually makes somebody a scientist, is the ability to have some insight into how to look at a problem. Here's how we're looking at this one. We're at the top of this mountain, and we're looking out at the horizon, and we're trying to figure out what that distance is. Maybe that's the wrong way of looking at it. You realize that if we're at a mountain right here, which is much smaller, and we're right there, our horizon will be in exactly the same location. As we move this closer to the horizon, we get to the point that our elevation will be 0. Yet, we can still see the top of that mountain. So, what I thought of was, what if I'm sitting right here and just my eyes are above the ground? My elevation will be 0. Even at a height of 0 right here, I can still see this spot on the mountain. I can't see any of that part of the mountain, but I can see the top of it. So, let's have a look at that. And quite frankly, our formula will be exactly the same with one minor exception. We're starting off at a height of 0. We can't see anything below a certain height a distance away. So our h, instead of being our observer height, our h will be the lowest part of that object that we can see from an observer height of 0. So going back to our original problem, if I'm 6 feet tall and I'm looking out at Lake Michigan, how far away is my horizon? 3 miles. However, if I'm 3 miles offshore and I'm treading water and just my eyes are above the surface, how high does something have to be for me to see it on the beach? 6 feet. Now, the reason that I thought about this was that many of us in the debunking community have had a look at flat Earth videos that claim they quote-unquote see too far, therefore the Earth is flat. Well, let's have a look at that claim. Now, when we see too far, is that truly a proof of the Earth being flat? No, it's not. It means that we have a different radius, because even without using the known radius of the Earth, simply by knowing the distance to the object and how much of that object we can see from the beach, we can calculate what the radius of the Earth is. Because one of the things flat Earth loves to do is they don't observe things from mountains. They observe things from a foot off the surface of the water. And they do that to take maximum advantage of refraction. But does that prove that the Earth is flat? Or does that just change the radius? Let's have a look at a classic example. Well, have we ever seen this picture before? Let's have a look at something here. First of all, the observer height, 1 foot. They're making a real big deal out of that. However, they also give the distance to platform habitat at 9.41 miles. So we have D. Now the question is, what's the lowest point on this oil rig that we can see? Obviously, there's tremendous distortion due to refraction. But let's look down at the bottom here. Here's the bottom of the rig. These are cross members. And then there looks like there's a solid object right down here by the horizon. Let's go see if we can identify any of these parts. So, here is platform habitat. Here is the bottom of the rig. Here are these areas where these crossbars are. And you can see those here. And then down here you can see a boat launch, but I don't see it anywhere here. I don't see this pipeline coming out. That seems to be below what I'm looking at. The lowest object that I can clearly identify looks like it's going to be the bottom of this cross-hatched area where these cross members are. I don't see anything down here. Now, another thing that I see is there's a watermark right there. There are watermarks here. This is all rusted. There are watermarks here. And there are watermarks out in this area. So that looks like it's the high water mark. This is obviously low tide. Let's go ahead and have a look at the permit documents for platform habitat. Now, this is rather interesting. Here is the water. Up to that boat landing, it's 15 feet above the water. And up to this area, it's looking like it's approximately 40 feet in elevation. The platform itself is 17 feet above that. So let's go back to this other photo right here. So it says that this is 40 feet above the water. Now we can calculate that out because a standard door is about 80 inches. Now it says that this thickness right here is 17 feet. And then it says from there it's down, looks like another 27 feet to the water level. We probably have about 20 feet of this platform missing. Let's be generous with that. It could be a little bit more. The curve calculator says it ought to be about 45 feet. But as I said, we've got a tremendous amount of distortion here. And I'm saying that we're missing about 20 feet of this platform. So let's go ahead and see what we have. Okay, so the distance is going to be 9.41 miles, which is what's listed on the Flat Earth video, equals 49,685 feet roughly. Okay? The height that we're missing is 20 feet. That's D. So let's go ahead and plug it in, see what the radius of the Earth is. So 49,685 squared minus 20 squared over 40. That will be our radius of the Earth. So let's go ahead and see what we have. Well, there we go. That gives us a radius of the Earth, and it's obviously really high because of all the distortion, but it's only 11,688.4 miles. That's about 3 times the actual radius of the Earth, and it's about 1/3 the radius of Jupiter, which is over 45,000 miles. So, what did they prove with their black swan? The only thing that they can actually claim is that they demonstrated there's a possibility that the Earth is a sphere about 3 times larger than we think it is. Now, Quantum Eraser and the others have put out claims that this means that there's a radius of 250,000 miles. Well, we just calculated it. It's less than 12,000 miles. It's big, but it's still a sphere. So, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by, and I hope that this method comes in useful, because you can use it in all sorts of these low-angle observations that they make where they claim that they see too far. Stay well, folks.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob, the science guy. science guy.